Okay, so let's continue on with this topic of combined loading and move it up a level into the 3D realm. Let's say we had a cylinder like I've shown here, and let's start by saying we could look at three different parts in the cylinder: A, B, and C. A at the top of the cylinder, B at that midpoint, C at the bottom. In essence, what we're going to develop is this new idea of looking at all the stresses at an individual point, now that we know that multiple stresses can exist at that single point. In order to do that, we're going to define a new variable. It's called a stress tensor. So in this case, let's say that we wanted to look at what's going on at point A. So what we could imagine, if we were to zoom in at point A, we could represent, in essence, a block at point A. And if I were to zoom in on this block, so it's like a microscopic view of what's going on in this block, what I can say are there are multiple types of stresses that can exist on that little element. This is still point A. So one would be if it's in, say it's in tension, right? Like I were pulling on the end of this cylinder and causing point A to be in tension. If that's the case, then I would say that I would have this side right here, and there would be a stress that would be pulling in this positive x direction. Now we said that if we have an axial stress we label as a sigma. And it would be tension or compression. And with this, we're going to have a new another new label technique, and it's going to be the subscript down here. And in this case, I'm going to have a subscript of XX. And what this subscript means is the first letter, so sigma XX, this is subscript. The first one would be the face. So what we mean by face is that is the perpendicular to my vector. So I can see that this face would be all along here because that is perpendicular to that axis. So the x-axis is perpendicular to the vector. All right, so let's erase those lines. And now the second letter is the direction that my vector is pointing. So in this case, I can see that sigma x is pointing, or that sigma is pointing in this x direction, right? So it's the x face, x direction. And I could do the same thing on this side over here. If it's pointing up, we would call that one sigma, and it's on the y face because the face of that cube that's perpendicular, or the axis is perpendicular to that face, is the y, and it's also pointed in the y direction. And same thing for this other face, I would have a sigma z face in the z direction. And a little hint, just by definition, you'd have to have either x, x, y, y, or z, z anytime you have a sigma, because sigma is an axial stress. Now, I can also have shear stresses happening at the same time. So with the shear stresses, I know that there could be one that is pointing, like, say, that way, and that shear stress I would label as tau, because we know that is the definition of a shear, right? The letter representing shear. And I say, what face is it? Well, it's still the x face, because that face of the cube is perpendicular to that x-axis. And then I say, what direction it's pointing? It's pointing in the y direction. So I end up with a tau x, y. And I could have another shear on that exact same face that is pointed in the towards the z-axis. So this would be tau x z. Now I can continue this process for all my faces and I end up with something like this. So what I end up with are 9 different stresses that can exist at this single point. My 3 different axial stresses with my sigma xx, yy, and zz, and then all these different tau stresses. So I need to figure out a way to represent all of these stresses, and this is where I am going to define this new thing called a stress tensor. So a stress tensor is really, in essence, it looks like a matrix, except a tensor is one level up. And I'm going to have all 9 of these stresses in this stress tensor, and it would look like this. I have sigma xx, tau xy, So that's what in essence the 9 element stress tensor looks like. And the way that I have this listed, you could probably already tell the first or the different columns represent the direction of the stress, and the face are the different rows. So we have faces and columns, and what that really does for us is it gives us this kind of this pattern where I have my sigmas along the diagonal, XX, YY, and ZZ, right? And then my shear stresses are moving away from that. Now, there is something else to point out here, and that is that if I were to look at an element with the shear stresses on there, and I were to put these shear stresses, what I have is tau, let's say we'll just do a 2D where this is X and Y, then this would be on the X face in the Y direction. And on the opposite face, I would have to have also, this is tau x y. Now, you might want to say, well, it's negative, but let's not get caught up on some semantics. I know that from some of the forces in the y direction have to equal 0 for static equilibrium. Those two have to be equal and opposite. Well, I also have to have rotational equilibrium. This would be a tau y face in the x direction, right? Let me erase this one, it's a little confusing. So what that means, or what this whole thing, because I have rotational equilibrium, what we can say is that my tau xy will be equal to my tau yx, and my tau xz would be equal to my tau zx, and my tau yz must be equal to my tau zy. And that'll always hold true. So you'll see some places will or some textbooks will actually only list this in numeric order because both have to exist. It also means that if we look at this stress tensor up here, if we have a tau xy, we find a tau xy, that means there has to be a tau yx value, and they have to be the same. Same thing with this xz has to be the same as that xz, and we also have this yz has to be same as zy. So what that means is we actually have symmetry about this diagonal, right? I mean, so you also see this sometimes where some textbooks won't even show the get rid of some of that stuff, won't even show the lower half of it, so they'll just show something that looks like that, and that's all you'll see because we already know what the other values are since there is that symmetry there. But for right now, we'll go ahead and leave it all on there. So I'm going to stop this video a little short. I'm actually going to break this into 3 separate videos because this is such an extended topic. So let me stop this topic here and pick up on the next video.